Okay, well, I hope you can hear me well, and I would like, first of all, to thank the organizers for this very kind invitation to give a seminar, which I accepted with joy, despite this happening exactly in one of the very few weeks I take for vacations. So the title of my talk is pretty straightforward. Let me tell you what exactly I want to discuss. Some reason I can't. Okay. I hope you're still there. Okay,
Yeah,
so this is what I want to talk. I will first tell you something about how you take a picture of a black hole in terms of observations. Once you take a picture, how you make a theoretical interpretation of what you've taken, and this really hinges around comparing theory and observations. And because I'm a theorist, and the seed of doubt is always there. Together with colleagues, we're starting to consider alternatives to Einstein and to black holes. So first, let me tell you about this technique that we've used, which is called VLBI. It stands for Very Long Baseline Interferometry. And there is a very simple expression that allows you to express the power of this technique, and is given here by this expression on the bottom left. If you want to reach a resolution, and this is a number you want to have as small as possible, then this is essentially given by the ratio between the wavelength at which you make an observation and the size of the telescope with which you're making such an observation. So if you take this expression face value, you would say, well,
sorry, Luciano, are you presenting in presenter mode? We can't see your presentation.
Okay.
We're just looking at you. Sorry to interrupt.
No, you have to interrupt me. I thought I am sharing.
We can see your presentation now. Well, it's gone away again.
Okay, let me try again. Do you see my presentation now?
Yes, we do. Maybe you can make that full screen or play it.
Now?
Yeah. Yes, that's perfect. Thank you.
Okay, all right, sorry. So it's the equation on the bottom left, wavelength over telescope size. You want this number to be as small as possible. So, you just say, well, let's use the smallest wavelength possible and the largest telescope possible. So this is very naive. Normally, very high frequency photons, very energetic photons get trapped. They are emitted near the black hole, but they get trapped. So they don't reach us in any manner. And so once you start excluding very high energy photons and you start going into radio wavelengths that you hope they can be observed, then you have to fight with another problem, and that these wavelengths are not absorbed, but they can be scattered. So to give you an example, suppose you look at the galactic center, and you look at the galactic center with a resolution of about 20 milliards seconds. This is shown on the left. What you would see is essentially a glowing emission with very little ability to look at the scales that are relevant, which are instead of the order of micro arc seconds. So in order to remove this glowing diffuse halo, you need to go to wavelengths which are smaller because their scattering is less severe. And so you do this by using higher frequency, and this means higher technology, because the frequency at which you receive your information is directly related to the ability of your technology to produce observations at this frequency. So if you go to just a few times smaller wavelength, you already start seeing that you can distinguish more detailed figures, of the emission. And if you go further and you start reaching a few hundreds of a microsecond, then you are starting to see really the emission coming from the source and not the ones scattered from whatever electrons are between you and the source. And what we wanted to reach with EHT was a resolution of a few tenths of a micro arc second. That was what we could afford. And then we were just crossing our fingers that given that resolution, we were able to actually see something on the scale of the horizon. Now, if the numerator of this expression is fixed, 1.3 millimeters, what about the denominator? You can think that, well, radio telescope, you can build them quite large, even a few hundred meters. There is a Chinese telescope which has a 500-meter diameter, but that would not be enough if you want to reach the microarc-second resolution that is needed. So the idea is to create a virtual telescope which is as large as the whole planet. And so what you do is you take telescopes, radio telescope, rather small size, 30, 50 meters in diameter, and you put them into this technique, the VLBI technique, which essentially amounts to connecting, say, a telescope in Arizona with a telescope in Hawaii, and do interferometry between the two of them. Now, this seems a bit bizarre, and there is a catch. The catch is that you want this telescope to be observing exactly the same wavefront, which means that you are not just recording an electric field in each of these telescopes, the receivers. You also have to make sure that the time of arrival of this electric field is identical. And that's possible because both these two radio telescopes have atomic clocks, which are then synced and allow us to align the two time signals and to do real interferometry. And of course, in this way, we have the possibility of connecting two telescopes, but then we could also connect more telescopes, say 3. And actually, it would be even better to have telescopes all over the planet. And that's because the planet is rotating, and so the source will at one point disappear. However, if we have sufficiently number of telescopes across the planet, we can always observe. And besides, having different separation between telescopes will allow us to see different length scale in the visibility plane, which I will explain in a second. So all you need for doing this is a bunch of telescopes. EHT doesn't own any of these telescopes. We have to ask in a competitive manner time on this telescope and then perform the observations. And that's exactly what we've done in 2017. So almost 4 years ago. And you can see we sent people in Mexico, in Chile, in the South Pole, Hawaii, in Arizona, and Spain. And if you look at these photos, you see that there is a common trait, and that is everybody is smiling. And the reason why everybody is smiling is because there was good weather. So this is paradoxical, but essentially we're trying to catch light that was emitted 56 million light years away. So it's taken 56 million light years to reach us. And then it's sufficient that you find a cloud 3 kilometers above your telescope, and you are unable to observe it because water vapor is the worst enemy for these wavelengths. So those were perfect conditions across the planet. Everybody had good weather, and so we could really do the best possible observations. We've redone those observations in subsequent years, never got as good weather as on the first try. So in 2019, the 10th of April, we published our result. This is the front page of a few magazines across the world, and you can see essentially it hits the front page of all of these. And it was calculated that in 24 hours, 3.5 billion people have looked at the image, which is a good fraction of the whole planet population. And of course, the merit is not scientific; it's really mostly due to the media, social media, that really grab the image and start making all sorts of interesting associations and pointing out effects we had missed in our analysis, of course. So let me go back to how you actually do these observations. As I explained, you need telescopes, and you need a number of them, and you need to connect them through VLBI technique. So I've shown you a realistic representation of the telescope that had been used in this campaign in France, in Chile, in Mexico, in Arizona, Hawaii. And I've marked with a color the baseline between these different telescopes. And as the planet rotates, each of these telescopes tracks a track in what is called a complex visibility. the definition is given above. It's a complex function. U and V are the projected baseline coordinates, and I is the intensity of the radiation that you're receiving. So think of this as a two-dimensional Fourier transform. And given a certain set of tracks, and so if you want the reconstruction at a certain set of wavelengths, of length scales, you obtain a certain quality of the image. And as time goes on and your tracks become larger, or if you want, as the visibility space gets more and more populated, the quality of the image increases. I will now show you a movie which does exactly what I've explained. As the planet rotates, the tracks are drawn onto this plane. Think of this as collecting Fourier information in frequency, but on discrete and detached intervals. And of course, because these are detached intervals, your Fourier reconstruction in time would not be perfect. And that explains why you see images which are not perfectly focused. Ideally, if this plane was perfectly filled, then you would see even the smallest detail of the image. So these are the images we produced out of the 8 days that we've been observing. Not all of them were perfect, but the large majority was very good. A few were bad, but then we decided to analyze these 4 days. And as you can see, within these 4 days are telling us a whole lot. First of all, they're not identical. And we expect that to be the case because the light we're observing is representative of accretion process. And this accretion process is only stationary on an average. And therefore, it can happen that there are days where the brightest spot is on the top left or top bottom right, depending on the conditions of the flow. But another important thing is that although they are not identical, they do maintain steady features like the size of the central depression, the size of the bright ring, and so on and so forth. And what I will next try and explain is what is it that we are actually seeing. Essentially, as a theorist, I was handed in this image and was asked to explain what exactly we were observing and how we could use these images to extract some physical information. So in order for doing this, you essentially need 3 steps. First one is performing GRMHD simulation. GRMHD stands for Generativistic Magnetohydrodynamic Simulations in arbitrary space-time. This essentially teaches us to understand what happens to matter that is falling onto a black hole. The second part is ray tracing and radiative transfer, and essentially amounts to, once you know how matter falls onto the black hole, produce an image from the emission that is coming from this very hot and energetic matter as it falls onto a black hole. And this is less trivial than you may imagine, and I'll explain you why. Because light does funny things in curved spacetimes. And the third part is, you can produce a very large number of synthetic images. These are theoretical images resulting from step 1 and 2, but at the end you want to compare with the 4 images that I've shown you and obtain some quantitative information about what you're observing. And all of this was possible thanks to some very generous funding from the European Research Council. This ERC grant that I was mentioning was given to me and to my collaborators, Mino Falken and Michael Kramer. And essentially, we use this money to build 3 computational infrastructures, BAC, BOSS, and GINA, that essentially do step 1, 2, and 3. And the real heroes in this story is not me or my colleagues, is really this team of very talented young researchers who have performed all of the hard work behind what I will present. I like to think about what I do in terms of equations. So the equations I need to solve for are, as I was mentioning, the equations of generativistic magnetodynamics. So I have an energy momentum tensor, I have to conserve it. I have a current of mass and I have to conserve. I have an equational state that will tell me how pressure and density are related. And my energy momentum tensor can be seen as the composition of all the ingredients I put into this into this plasma. So we'll have an electromagnetic part associated with the electromagnetic fields, a fluid part, and of course, if I have an electromagnetic part, I will also have to carry out conservation of Faraday tensors or the Maxwell equation and so on. And I need to be able to solve these equations in full generality and in a curved space-time, which is not necessarily that of a curved or black hole. And in addition, I need to, as I explained, track how light is produced in any place in this accretion flow, then can reach an observer. And for this, I need to solve a radiative transfer equation, which is given here, which is essentially the Boltzmann equation for a distribution of photons. And of course, I will have some emission property, I will have some absorption property, which all I have to take into account. To give you an idea of what happens, I'll show you a sample. This is a simulation of a curved black hole accreting. The spin is 0.93. I'm using Kerr-Shield coordinates so that allow me to go inside the horizon. And you start with a torus of plasma, and then this torus very rapidly produces an MRI, a magnetorotational instability. This is really what drives matter to accrete onto a black hole. As you can see, the distribution of matter is not on a thin disk. So we know that under the conditions we observe this object, that we cannot have a very thin disk. It has to be rather geometrically thick disk. And what you can also appreciate is that the accretion process, because it's driven by an instability, is not steady. It's turbulent. And so there's going to be times where you have a lot of matter accreting, other times where there is less matter. And of course, this will introduce variability. Imagine you are next to a waterfall. The waterfall there is going to have times where there is a lot more water falling in, and times where there is less. This is the inclination which we think we are observing M87, the center of this supermassive galaxy. In blue, I'm showing what is called the magnetization. So you can think that there is a lot of magnetic field in that direction. This is what you would observe if you were to see with 1.3 millimeter sensitive eyes. You would see essentially a ring of light, but this looks very symmetric. However, this is just a matter of our fortuitous inclination. If you see things from a different inclination, you would see a much more complex field, and I'll explain you why. And this is what you would observe if you add now radio telescope, which have a finite visibility and resolution. So, and this is what we observed. So as you can see, when we saw the first observations, we already had a pretty good idea of what is actually happening here. And this is just to give you an idea of our of what we actually simulate. It's a very small torus, much more large jet. Okay, I think I am stuck again. So I've explained that you need ray tracing because light doesn't propagate on straight lines in a curved space-time. And suppose you have a black hole and you have a thin disk. As I said, we don't have thin disks. Let's suppose we have a thin disk which is emitting light, and you want to take a picture of it at a given inclination. So this is like a photographic plate. Well, then you're going to get all the photons that come you on a straight line, and these are the ones on the direct image. But of course, you can see also photons that are behind the black hole that would go otherwise, would never reach you, but because they are bent by the black hole, would allow you to see the back part of the disk. And to make things even more complex, you can actually see photons that are emitting below in the lower sheet of the disk. And because they are bent, they can reach you. And of course, this is an image that you all have seen. And this is, the Interstellar movie. So in the Interstellar movie, if you ever ponder what is it you're actually seeing, you're seeing the part of the disk which is right in front of you. You're going to see the part of the disk which is behind you. And you actually see also the part of the disk which is below the disk, and you can still image. And something you have to bear in mind is that this is an idealization. the disk is not thin, and there are jets that are not shown in this picture, but are also producing light and need to be considered. Now, what we've actually observed is not but the shadow. This is a group of relativities, so this will be very easy for you to understand. Suppose you have again a black hole and a source of light. This source of light will produce photons. Now there's going to be photons that are going to be immediately captured by the black hole. These are those that hit within the Schwarzschild radius, but there's going to be photons that are within the capture orbit of photons. So they are within the unstable circular orbits, and they will not hit the horizon right on, but they will be captured eventually. And so if you're an observer at a large distance, what you see is a deficit of light. There is a region where light is just lacking, and this is lacking because it is intercepted by the black hole. So just to give you an idea about the dimensions, the event horizon is 2m, the photocircular orbit is at 3m for Schwarzschild, and the shadow is essentially the radius is the impact parameter at the photon circular orbit, and so is of the order of square root of 27 or 5 point something. Something you should also appreciate from this cartoon is that the shadow is not necessarily black. That's because if you take a photon where my cursor here is, and you send a photon outwards, this photon would have no problem reaching the observer. So the shadow is just a region where you expect to see a depression in light, but is not a region that should be dark. And of course, if you, well, let me go back to this picture. If you, okay, I will use this one. There is going to be a dependence on the inclination. So if you, depending on inclination of the observer, if you are looking it right from the top, then you will see a perfect image. But in any other angle, in particular, if you're seeing edge on, you will see a much more complex picture. What you will see here is the edge of the shadow, or what do we call the light ring or photon ring. And I've explained all of this so you have an idea, but again, let me be clear. We don't think that we see a thin disk. Given that the plasma condition, the disk has to be optically thin, so the light can go through it, but is geometrically thin. And so what you are expecting to see is more something like what I'm showing you here. I'm now showing the emission from a thick disk, and I'm just changing the inclination of the observer. And as I was mentioning, if you're seeing it face on, you would see a perfectly symmetric image, but in any other conditions, you would see the presence of a shadow and also the presence of a bright spot. Or if you wanted, and thinking about a ring, there's going to be a part of the ring which will be brighter than the other. And the reason for this is very simple. This is Doppler boosting. Light coming from this region is moving towards us, and so will be Doppler boosted. And that explains why in the picture I've shown you in the beginning, we see that the bottom part of the image is brighter. That's because there is a certain inclination, and this inclination is making us see there's going to be a Doppler boosting, and so we see that part, and then with respect to the top part. So these are basics. These are independent of any consideration. But as a theory group within the AST, we had to explore all possible space of parameters. And there is a space of parameters going to do with plasma dynamics, or black hole mass and spin, and the accretion type. The accretion is generically coming from a disk, but then depending on the property of the magnetic field and how it is distributed in the disk, you can have what we call sane accretion, where sane stands for standard accretion, or MAD, which stands for magnetically arrested. So these are two possible modes of accretion, which will produce slightly different phenomenology. In particular, you will have thinner disks and slimmer jets, or thicker disks and broader jets in MAD. Then we need to determine, describe the dynamics of light and its properties, and so the mass and size of the shadow in terms of the black hole mass, the microphysics of the emission, the orientation with respect to the observer. And then we need to take into account information that we have prior to our observations, which has to do with the black hole mass. There were other observations of M87, which had produced some estimate on the mass. We knew what the inclination was. We knew what the X-ray luminosity was. We knew what was the power in the jet. So all of these are additional information that we could either use or decide not to use. Now, I think I will skip through this quickly. Electron thermodynamics is possibly the most delicate aspect of all of our modeling. We need to decide where is the light produced. We know that the light has to be produced by synchrotron emission, so electrons are the responsible for this. And of course, if you remember how synchrotron emission works, you need a certain energy distribution in the electrons. We don't have this information because our simulations do not give us the temperature of the electrons, give us the temperature of the ions, the heavy part of the flow. So we need to relate the temperature of the ions that we know from simulation to the temperature of the electrons. And once we know the temperature of the electrons, we have to decide what is the distribution. We have been very simplistic and actually not so crude, and created a very simple relation that relates the ion temperature and the electron temperature through some parameters. One of them is this R high. It's just a tunable parameter. And what is called a plasma parameter. This is just the ratio between the gas and the magnetic pressure. And essentially, by playing with this free parameter R high, we are able to provide emission coming mostly from the disk or mostly from the jets, or a combination of the two. So there is no way out, since we don't know the energy distribution of electrons, but to have a phenomenological description of what is their temperature. And we have explored this by changing this parameter. So we have run a number of simulations, as the one I presented. About half of them have been performed in Frankfurt. Then for each of these simulations, we built a number of scenarios. That is, we changed the prescription for where the light is produced. And this is just giving you a very crude description of the space of parameters we have explored. So as you can see, there are situations where we have very small shadows, we have very large shadows, we have flows that is coming counterclockwise with respect to the black hole spin, or in the same directions. And for each of these simulations, we produced images. An important point, which I think has to be stressed, is that we don't really know, given an image, where the light is emitted. So this is an example of some images. The top two are produced from a MAD simulation, the bottom from a sane simulations. They differ by the values of this parameter, how high. And because it's just synthetic, we know everything about them. We can decompose them. We can decompose the part that comes from the midplane, so the disk, or the part that comes from the jet coming towards us, or the jet that goes away from us. This is also maybe a bizarre concept to digest. We see light also from the jet that is moving away from us. And that's again because it's just bent towards us. And as you can see from this matrix, it's very hard to tell where the light comes from if all you have is the first column. And that's because depending on the model and depending on the emission that you are considering, the light could be mostly from the midplane, or if you see the bottom right, could come mostly from the far side jet. So if you give me an image, even if I have produced it, it's very hard for me to tell where light is. Just imagine how difficult it is to tell where light comes from the actual observation. So this is one of the aspects of this whole business that you have to appreciate. There is a certain amount of degeneracy in the modeling. Out of these different scenarios, we built about 60,000 images, and this is now step 3. We had to compare the 60,000 images with the 4 images performed. And there are many different ways of doing this, but to give you a flavor, this is an image from a simulation on top, bottom left. This is the same after you deconvolve with the uncertainty in the observations coming from finite size telescopes. These two images can be compared and decomposed. In particular, these are the synthetic ones. These are the data, the blue ones. And these can be decomposed into visibility, amplitude, and closure phases. These are the two pieces, the real and the imaginary part of the visibility amplitude, the concept I've given you, the Fourier transform I was giving you right at the beginning. And so we have 60,000 of them, and for each of, and then we have the data, which is the blue data. And so each image will produce a certain, chi-squared, a certain fit to the actual data. And then you can just organize all of these 60,000 images and organize them in chi-square distributions and decide which ones are fitting best. Now, this is an example. The left is observations, the right is theoretical model. And when you see something like this, you think, wow, I know exactly what we're observing. Because on the right, you know everything about the property of the model that has produced that. Unfortunately, this extremely good match between observations and theoretical model happens way too often. So this is an example. On the bottom row, you have three images. These are synthetic images, and these are deconvolved from the top row, and they give you exactly the same match with the observation, but they correspond to completely different objects. This is a sane accretion model of a counter-rotating black hole. The mid one is again a sane, but for a Schwarzschild black hole, and the right one is a MAD with a co-rotating black hole 0.94. So this is a clear indication that there are degeneracies. This is both good and bad. It's good because independently of this detail, you know that there are some features which are robust, like for instance, the fact we are observing a black hole. The bad thing is that, of course, you are insensitive to things like the spin, given the quality of the data, the present quality of the data. And in fact, we don't give any measurement of the spin in our paper. We just say this is the most important measurement that we give. We give the mass of M87 star, which is 6.5 billion solar masses. And you can break the degeneracy I was just showing here by inserting additional information. For instance, we know what is the X-ray luminosity of M87. We know what is the jet power in M87. If we use this additional information, then we can break this degeneracy. And for instance, exclude Schwarzschild black holes from this picture. We cannot remove all of the degeneracy, but we can certainly make some cleanup. We haven't decided to do this because this is what we actually measure in our observations. Okay, I have to go a bit fast here. So what we've seen is perfectly compatible with the simplest explanation, which is a curved black hole in generativity. But this is an observational science. We cannot control what we observe. And so there are degenerate explanations that are possible. And if you want now to start testing gravity, this is not trivial if you have hundreds of possible options. And you can use both an agnostic or agnostic approach to exclude or allow for alternatives. Let me tell you a little bit about an agnostic approach which I developed. Luckily, we don't need any field equation. So, I don't need a Lagrangian. All I need is a metric because I can exploit equivalence principle and therefore, because I'm talking about test particle motion, be it of the plasma or of the photons, all I need is a metric. And so we have developed an agnostic approach, which is called the RZ or the KRZ metrics, to express generically static or stationary black hole spacetime. Essentially, you express a generic metric G mu nu in terms of a certain coordinates and coefficients AI and BIs. And of course, if AIs and BIs are equal to 0, you take GR as a limiting case. These are all perturbations around GR. Now, there are many other approaches. I think this one is particularly successful because it uses two mathematical tricks that I knew from other contexts. The first one is that we use a coordinate compactification. So rather than using radial coordinates, we use a compactly defined coordinate. So instead of going between 2 and infinity, we just go between 0 and 1. And another important trick is to use a continuous fraction, or if you want a Padé expansion at the horizon. All of these metric functions you can think of will be divergent at the horizon. So why not use an expansion that is a continuous fraction that is particularly well suited to handle poles like Padé? And this is an example of a continuous fraction. And the beauty of this continuous fraction is that you can truncate the expansion exactly in a given order. So if you say A3 is equal to 0, and all the other coefficients are automatically 0, and you just retain the first two and so on. And
Luciano, sorry, you've got 5 minutes left.
Okay, very good.
Okay.
So you can test this, and it's amazingly effective. And with 2 or 3 coefficients, essentially you can reproduce any known metric, be it static or stationary. So what is the agnostic approach? Well, is you start saying, okay, I have a given black hole or a given object who is not a black hole, and I start testing whether this black hole satisfies the observations. So already before obtaining the EHT observations, we have explored this, and more recently with Prashant Kochar-Lakota, we have done this within the EHT. So if you want to compare two black holes, the first thing is to compare apples with apples. And of course, how you do this? Well, you have to decide which of the black hole quantity it's more important for you. It can be the size of the horizon, it can be the location of the light ring, it can be the location of the innermost stable circular orbit. And in the case of this comparison, we have considered dilaton black hole. It was a spherically symmetric, so the only parameter was a dilaton field. And by tuning the dilaton field, you can reproduce a Kerr spin, say 0.6. So suppose that you want to compare a Kerr black hole of 0.6, you just have to tune the dilaton parameter so as to match the horizon size, the photon orbit, or the ISCO. I will not go through this because I don't have the time. Let me just show you the end result. This is the imaging of a Kerr black hole on the top, the dilaton black hole at the bottom. If you stare these objects fair enough, long enough, you can find differences. If you start putting in scatter, which is something that certainly will plague us with Sagittarius A star, you will start seeing that these differences are still there, but are much more difficult to distinguish. So the conclusion, the fair conclusion is that right now, given the present ability of our observations, we cannot really distinguish black holes. Or better, we cannot distinguish two types of black holes. And that is why the title of my talk is the first image of a black hole. I haven't said the first image of a black hole in GR. So right now, I don't believe anyone claiming that has seen a black hole in a given theory can be considered serious. You can come up with other alternatives. What if it is not a black hole? What if it is something that's as a photon orbit, so can produce a shadow, but doesn't have a surface? For instance, a boson star or a boson condensate. In this case, I will just show you very quickly what happens. It's something very interesting. If you accrete onto a boson star, the boson star doesn't have a surface, so matter can go right in. It can't go to R equal to 0 because it will start developing a very strong centrifugal potential. And so we'll produce a condensate of plasma at the center, a mini torus we call. And so the emission from this mini torus will decrease overall the size of the shadow. This is an example of an image of a Kerr black hole and of a boson star. And once you introduce, this is assuming infinite resolution, once you start introducing a resolution coming from the instruments, you see that the boson star would have a much smaller shadow. And of course, the shadow is proportional to the mass. And so you can you can increase the mass and have a shadow as large as you want. But then in the case of M87, it cannot be a boson star, because if you want to increase the mass, then this would be incompatible with any of the mass measurements we've seen. So boson stars can be distinguished from black holes. And in particular, in the case of M87, we have excluded the presence of a boson star. So let me come to the conclusions. Black Hole Camp, this European project, has played a major role in the HT campaign and analysis. We have looked at many different properties of accretion onto occur black holes, and had to learn a number of things which you didn't know before. We are now starting to explore alternatives to occur black holes, and we've looked at boson stars, which can be distinguished, while other black holes in other theories cannot. So if you ask me what is one of the most important contribution of DHT, I would say, well, it has provided the first evidence of the existence of supermassive black holes at the center of a galaxy. And you know, this was something that you have learned in the first course of astronomy. Supermassive black holes are at the center of galaxies. But now we have the evidence, at least, that in one galaxy, such a supermassive black hole does exist. But personally, I think the most important thing is that we have transformed a concept, that of the event horizon, into a testable object. And this is a very valuable first step in any science, the ability of using observation or experiments to confirm or refute a given theory. So thank you for your attention, and I hope I haven't gone over time.